Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today's theorem is actually a very nice one. It's not very hard to prove in the end if you know the idea. It's still very, very beautiful, and I call it elliptic addition, which certainly is not the standard name. So be a little bit careful here. But kind of the idea, as we will see, is pretty natural in some sense, very geometric in nature, and it's one of those very surprising moments in the history of mathematics where people started looking at something that was nice from the viewpoint of maybe number theory or geometry, or maybe algebraic geometry in this case, but there was no really any good reason why this should be useful in practice. Turns out that this is well, really useful here. The elliptic addition is one of the cornerstones of modern cryptography. I will explain that at least briefly at the end. So, the point here will be those Torus games. You might know some of those Torus games. Those are usually the games that are kind of played on a Torus. So a lot of developers are a little bit, so game developers are a little bit lazy. And if your world is just big enough, and it kind of doesn't matter anymore, so you kind of don't have a spherical world, but you more have this toroidal world, like on the Torus, where when you leave to the right, you actually enter back to the left. And when you, let's say, leave to the bottom, you enter back from the top. So that's not a sphere, that's actually a torus. And a lot of games, as I said, take actually place on a torus because the developers are a little bit lazy. And it's just much easier because it's flat. The torus is flat. It's much easier. Let's say something where you have where somehow the game wants to simulate the world, so the Earth, and it's just much easier to make it flat, such that you can leave to the right, you actually enter back to the left, and if you leave to the bottom, you actually enter back to the top. In practice, it usually doesn't matter, but it's kind of fun. And the older games, where the worlds weren't just very big, and you were just not able to see it anyway, so most modern worlds are just so huge that you might not even recognize that it's a torus world. But the older worlds from my generation, so ages ago, prehistorical times, where it just was one screen and it was kind of obvious. If you left to the right, you entered from the left, and if you left to the bottom, you entered from the top. Anyway, we will see something similar, and it will be a lot of fun, I promise you. But now let's just jump right into it. So the idea actually comes from, as I said, something like number theory, elliptic geometry, algebraic geometry, elliptic curves. So what is an elliptic curve? An elliptic curve is basically a solution to an equation like this. So y squared equals x cubed minus x, for example. So you know all these solutions to these equations. So for example, if you would have something like x squared plus y squared equals 1, and you're looking for the solutions to the zeros of this equation, you would get a circle. So this would be the defining equation of a circle. And these are just a little bit more fancy, those elliptic curves. So for my talk today, it's totally fine to think of them as being of this form. So y squared is not related to x squared, but it's related to an x cubed and some multiple of x and maybe some constant b. For example, this one here, of course. And it's not quite looking like a circle, but it has some nice, some nice shapes like this one, for example, or like this one. Show you in the Mathematica animation in a second. And you usually, for practical purposes, you will see that in a second, you also have this point at infinity, which is kind of an additional point. So it's not just the solutions to those equations. So in, let's say, in whatever kind of field you prefer. So in those pictures, of course, you have solutions in R2. Some people like to work in other fields, whatever. We'll see other fields later. But for now, it's just totally fine to think of this as a Euclidean plane. So not just those solutions, but also this funny point at infinity. And as I wrote here, with a bit more care here, you can actually define this over any field. I will use that later, but let's not worry about the details here. Everything is linked in the description anyway. But let's have rather a look at how those elliptic curves usually look like. So here's my Mathematica demonstration, and I have my elliptic curve given exactly by the equation from before, and I can vary a and b. So a was the factor in front of x, you will see that in a second anyway again, and b was the constant. And as you vary this, so Mathematica is a little bit slow, it doesn't look really smooth, but it actually is. So the curve kind of changes, And it might change a little bit drastically. So if you move B, oh, it creates a new component here. As you can see, does something funny. And if you move A a little bit, creates a little bit like this, right? So you can move those coordinates. And depending on A and B, you might get quite different looking shapes. So let's say this one here was a X-shaped type thing. I have no idea what it is, to the left, and kind of a little bit like a pergola to the right. And if you vary B a little bit, then it kind of merges and it might get completely flat, something like this. So that's a blueprint example of an elliptic curve or a family of elliptic curves. Okay, and it's not quite obvious why this should be really important. In some sense, I would like to think of these equations as generalizing the equation for the circle. So it's kind of the next step in complexity away from the circle. So they might be very interesting. Slight bummer here, so slight warning. They're not really related to ellipses. They're just something different, okay? I will link in the description where the name elliptic curve actually comes from. Not related to ellipses, but still I would like to see them as a generalization of a circle in a certain sense. And then comes the main observation, which is really the main player, a beautiful observation. Simple, easy, powerful, we'll see. So let's jump right into it. So there is actually an addition on an elliptic curve. And this addition will use the point of infinity. That's why you kind of want to have it. And it's a very easy, really, really easy idea. So let's say you would like to add points on the curve. So that's our solution set, right? The points on the curve is our solution set, and you would like to have an addition on the set. And it turns out that this will be really, really a nice addition in the sense that it will form an Abelian group. The formal terminology here is that they're Abelian varieties. So they kind of have, it's kind of just saying they have an addition and there is some geometry going on as well. Anyway, so let's have a look at the addition. So you fix a point P and you fix a point Q and you want to add them. And this is what you do. You just draw a line between them. So here's Q, here's P, you just draw a line between them. My line is not very straight, but you get the point. In the picture, it actually is straight. Way. And this line will intersect the curve in a different point. And you kind of want to call that point P plus Q. But there's a sign error, so it's not quite P plus Q, but the mirror along the middle axis is P plus Q. So let me comment on that in a second. Let me comment on that. So this equation tells you actually, because y squared, so y is going in this direction, is something in x. This tells you that there's a symmetry of the curve given by mirroring around the x-axis, and that's what you use here. So instead of using the direct intersection, you use actually the mirror point down here. So P plus Q would be down here. So let me show you some other examples using Mathematica. So here's Mathematica demonstration. Of course, everything is usually linked in the description. It's kind of the same setup. It tells you what kind of point you have chosen here, P and Q, P plus Q. And it tells you what kind of curve you have, so you can vary here your values of the curves, that you vary the curve, whatever. Let's stay with this one, for example. And then you can vary your position of P. So P here in this picture is very far up here. So let's pull this a little bit down. So as you can see, P is here. And now you can vary the position of Q. Well, let's put Q here. And it's this idea that you intersect them, you draw a line between them. This will intersect the curve at one point. You mirror it down. That's P plus Q. Let's have a look at another example. This is too far away. Somewhere here, maybe this is too far away. Somewhere here at the very top of the picture. And now it intersects almost here to the left-hand side. So P plus Q is here. Let's change the curve a little bit. So P, Q, P plus Q. I think this is pretty beautiful, right? Pretty beautiful idea. A geometric addition. Just draw a line between your points, see where they intersect the curve, and we're ready to go. I show you more examples as we go along. In particular, you will see where the point at infinity comes into the game. And this gives kind of the point here. This gives rise to an Abelian group depending on your field, depending on your curve. So I call it E of K, depending on, well, there's some K, some underlying field, as I said here. These are just real points, but there is no really any reason to restrict to the real numbers here, unless you want to draw pictures, which is not quite true. So let's have a look at the finite case. So here's a finite case. The finite case is extremely interesting. It's by Torus game. I'll show you an animation in a second. So it's the same idea. You have an elliptic curve and an elliptic curve over a finite field. So here my finite field is, well, the prime field with, well, the prime is 97 here. So it has 97 points, and it's addition and multiplication mod 97. So 97 is kind of the biggest, 96, strictly speaking, is the biggest number you see, and 97 is 0 again. And in this case, the curve is more like a cloud of points, because there are only finitely many of them. You can still see this kind of the symmetry mirroring around this axis that's still there. And the idea of adding points is really, really the same, but in this Torus game world. So if you have an A and B, and it's kind of a miracle that it works, because now you're staring not at a smooth curve, but actually at a set of points here. But it still works, kind of fun. It's kind of built into the equation that this works. So take your point A. So point A is any point of your cloud here. Take a point B, any point, any other point of your cloud. Draw a line between them. And, well, it should intersect the curve somewhere. And now you play your Torus game. So you exit to the top here, just continue the line, enter back from the bottom. It still doesn't intersect the curve, You hit the right boundary, you exit, you come back from the left, and you actually hit a point here, you mirror, and you get C. And C in this case is, of course, A plus B in this notation. Kind of a fun thing. So let's see that actually in an animation. So here's the animation. So A, you connect it to B, you play your Torus game, and at one point you hit the curve, you mirror down, you get C. Another one, A, B, you connect it until you hit the curve, you mirror down to C. Absolutely beautiful. Surprising, beautiful, amazing, always works. Kind of beautiful. I can't say anything else. It's just so great. And you get kind of very funny abelian groups. So here, over a field with 72 elements, so 72 is not the best prime in the world. It should have been 71. So over the field with 71 elements, the curve x cubed minus x is actually of this funny form here. So it has 72 points. So that's where my typo comes from, because it has this point at infinity still. So not just 71 and 72. And it turns out to be Z mod 2 cross Z mod 36. And it's absolutely not clear which one you get. And that's kind of the point. You get really, really crazy or complicated abelian groups from a given elliptic curve. And again, this Torus game addition is just so much fun. It's just really beautiful. And then the statement itself is that this actually works. So this gives rise to an abelian group structure where our fancy point at infinity is actually the zero of this abelian group. Kind of a little bit of a funny fact here. So the infinity here is 0 in this game. So the identity is this point at infinity. And the rules of the addition are summarized here. So if you have P and Q, then this point R is actually not quite the point. P plus Q, it's minus P minus Q. In other words, you have this relation. So P plus Q plus R equals 0. And then there are some exceptional cases depending on how your tangent in this case looks like. For example, you could have P plus P, and in the case P plus P, we would just get P plus P is 0. So P plus P is self-invertible in case P sits very nicely, for example, it's this outermost point. So up to some exceptions, which I summarize here in 2, 3, 4. It's really the addition that I showed you works over any field, finite fields, whatever, something like that you would like to use here. Pretty beautiful. And the unit of this addition is the point at infinity. If you think about it a little bit, it's actually pretty clear. Kind of the way the addition is defined, the unit will be the point of infinity, and that's why you want it. That's why you add it in the end. Beautiful theorem. I just told you how it works. Now it's really not so hard to prove anymore. The main meat is associativity. So that's not so easy to see, but if you just write it down, it's actually not so bad. Beautiful theorem. For every elliptic curve, you get a nice addition. You need to get a nice abelian. And it turns out that this abelian group is kind of my story here. It turns out not just to be interesting from the viewpoint of geometry and number theory. It's kind of obvious that it should be interesting from the viewpoint of geometry. Why number theory? Well, those curves turn up in the solution of Diophantine equations. So think about Fermat's last theorem, looks very similar. So we have curves that look very similar and so on. So yeah, these are really, really interesting from the viewpoint of number theory, and obviously from the viewpoint of geometry, but from the viewpoint of cryptography, that's not so clear actually why it should be true. But it turns out that is, I think at least, so if you're watching this right now from one of the standard browsers and it's not super outdated, then the standard browser will actually use the key exchange based on elliptic curves. So in some sense, the very popular algorithm RSA is a little bit outdated nowadays, and it's just, so this analogy that I found is roughly breaking the same amount of, so in this case, 228-bit of this RSA, which basically needs a little bit less energy to boil a teaspoon of water. Breaking the same as obtained from an elliptic curve would need quite a bit of energy. This, of course, just a little bit hand wavy and so on, but it should show you, or it kind of illustrates how much better, in some sense, elliptic cryptography is compared to the classical algorithm. And that's why most computers will use it nowadays. As I said, if you're watching this now from one of the standard browsers, it's quite likely that your standard browser actually uses this form of cryptography. And in the end, it's just really the same as the usual RSA, which I'm not going to repeat here. So link to everything is in the description anyway. But the point here will be that you use this fancy abelian group structures, which are not so easy to guess from the elliptic curve itself, and use the addition instead of the usual addition or usual multiplication that you would use in the RSA algorithm. So kind of what you get is the following. So there will be a public point, so like the public key, and there will be a private point, so a private key that's just an element of n, and then we will have the public key, which is just p added k times. And to undo this operation is actually not so easy. That's the whole point of this part of cryptography, and can be done over any funny finite field. As I said, it's pretty useful in practice. Okay, let me wrap up. There is this really beautiful idea, just using an elliptic curve to get an addition running, just by intersecting basically the elliptic curve with certain lines. And this addition gives you rise to one of our favorite structures, an abelian group. And those abelian groups are a little bit fancy. They're not so super easy to compute. And that's why they turn up to be very useful in cryptography. I like to repeat it. So probably while you're watching this right now, somewhere in the background, there's some elliptic curve cryptography running based on this really nice addition, which is amazing because people really just studied those from the completely abstract viewpoints of geometry and number theory. Anyway, I hope you enjoyed the video, and I also hope to see you next time.